we will start right in. Hi everyone. To our first talk in the new series, in our 6th series of the EDT.Community seminar sessions. Today we have the pleasure to hear a talk from Cláudio Gomes. But before that, we also have as an introduction, here we go. We've collected some publication target that could be interesting for you interested in digital twins. There is, with no deadline yet, the Modit workshop, as in the last 2 years as well, co-located with Modulus. There will also be a workshop particularly for AI for digital twins and cyber-physical applications at this AI conference, where the deadline is beginning of May. And then at the end of May, there's also a workshop on digital twins for business processes. So if you're interested, here are the links. We can also put them somewhere on the website afterwards. But let's circle back to our seminar series. In this edition, we start off today with a talk by Cláudio, and then we will also in the upcoming weeks, in our 2-week schedule, as always, we will have in 2 weeks another talk by a scholar from TU Eindhoven. And then we will have 2 more industrial talks in this series from two people from Algorix, physicists from Algorix actually, and then also 1 colleague from Aarhus talking to us about what they will do related to digital twins. And then, as always, we will conclude with this panel discussion. But enough advertisement. Today we want to. Today we hear from Cláudio. Cláudio Gomes, he's an assistant professor at Aarhus University. He's also part of the Digit Center at Aarhus University and member of the standardization committee of the FMI standard. And his research focuses on his main research. Let's say is about interdisciplinary work on promoting the engineering of digital twins, just like we are promoting the digital twin engineering in this community. And today we will hear about his most recent work, where he's focusing on uncertainty quantification. And in this case, it's uncertainty quantification and propagation in digital twins. So with that being said, I'm very much looking forward to what Cláudio has to say to us today, and I will hand over to you.
Thank you, Daniel. Hi, everyone. Thank you very much for making the time. I know this is the end of the day for many. I hope to give you an entertaining 1 hour. So I'll start sharing the screen. I can use this thingy with, yeah, the laser pointer. So the plan is to give you a couple of examples of uncertainty quantification and propagation. I've abbreviated this because it's too difficult to pronounce it all the time. Then I'll introduce an example. So first I'll start with a traditional uncertainty quantification and propagation. Then I'll introduce an example to digital twin, and I'll describe an example of uncertainty quantification and propagation in the digital twin context. And you'll see the idea is to have a nice discussion comparing the two later. And we'll take then a step back and take a broader view at uncertainty in self-adaptation, which is one of the core services of digital twin. We'll be guided by example. As Daniel said, we work very much with real systems, and we try to solve the problems in those systems, and we try to apply best tools and create our own tools in these systems. So we are very much driven by examples. Let's imagine we have a small version of this agricultural robot, and imagine it's supposed to drive through cabbage field, right? And it's supposed to drive in a straight line, right? We don't want it stepping on cabbages. So this robot can be summarized as a system comprising a plant, the mechanics and so on, the stuff that's not software in the robot. And then we've got a controller, which is the controller of the robot. And we have some environment, think of wind and so on. And the job of the robot is simple. We're simplifying the scenario. It's just supposed to drive on a straight line from left to right. Right, so the controller is relatively smart. If I position the robot outside the field in a particular orientation, the controller knows it has GPS sensors, right? So it knows where to drive the robot, so it starts going in between the cabbages. And what you're seeing here is the picture of one wheel of the robot, right? So this is this is the one of these stretches, straight stretches, right? So this is our ideal behavior, but in practice, what we're going to observe is, if you zoom in, you're going to see that it's actually not so clean after all, because of all the noise, of all the uncertainty in the system, and you'll see that it sometimes steps on cabbages and so on, which is okay. You may agree with your client, with a farmer, that a certain probability of stepping in cabbages is acceptable, right? So that is the that is our example. A property of interest. So the method to quantify uncertainty is to first define the events of interest and make sure those events are identical, independent and identically distributed. So let me, So what we have here is we're defining two events of interest. One is a maximum violation where it stepped on a cabbage. So how much did it actually penetrate the cabbage field in one of those deviations, and how long did it stay out in the cabbage field? So these are the two events of interest. And by the way, these are not independent, right? You can see that if the robot crosses a field and then comes back into the normal path, it is still more likely to exit the field. But the more time, the trick here to make them independent is to consider longer stretches of time, because the more time passes, the less, the more independent the second violation will be from the first. So we can consider stretches of time of 1 hour, for example, and then take the maximum violation and the maximum duration in that period. That's how we make these events independent and identically distributed. So this is our methodology. We define our events of interest, and we have to be careful with this IID thing, because we're going to compute statistics based on that. Second, we will do physical experiments, right? We go into the field, we drive the robot, and we have the GPS, and we start measuring the robot stepping on cabbages, and we take measurements, right? That's going to look like this, except maybe a lot less data, because this stage is naturally very expensive. I'll describe later how we can take shortcuts on this. But each of these trajectories is a straight run of the robot. And for each of these trajectories, you can look and quantify the maximum violation occurred, and quantify the two events of interest. So the peak, so the maximum displacement on the cabbage field, and also the duration, how long it took driving on the cabbage field. So we count these, and we can put them in histograms, right? So we see a maximum peak per experiment. We create these bins, and we count how many occurrences of the event of interest has occurred in the total, in this total number of simulations. So for example, violations of maximum peaks of 5 centimeters, we can see 250, let's say 1,000 simulations where 1,000 experiments were conducted. We'll later discuss the simulations. 1,000 experiments were conducted. Then we've got 260 more or less achieved the maximum peak of 5 centimeters. And then we've got another 200 achieved a maximum peak of 10 centimeters, and so on. So we can compute this, these statistics, right? This counting. And we can now normalize these counts, turn them into probabilities, right? And then identify, okay, once we have these are now probability density functions. So we need to find what is our statistical distribution that better explains the data observed. So we look at different probabilistic distributions, and maybe gamma distribution is a good one. And we see, for this particular parameterization of the gamma distribution, we actually have a fairly good fit with the data, right? And then we can fine tune, we can naturally fine tune these things to match the data. We do the same for the second event. Again, gamma distributions looks good. And we select, we manipulate the parameters of the gamma distribution until it will roughly fit the data. Right. So what do we have so far? A bunch of data, lots of time wasted on these physical experiments, but we have probability distributions. So we have quantified the uncertainty of the violation of the events of interest, right? So what we can use this for online monitoring, right? Let's say we conducted these experiments well, here in Denmark, and then the robot is in the field, and each time the thing we need to do is identify the operational data that matches the experiments, right? We need representative robot traces that match what we've done in the experiments. So in this case, stretches where the robot drives in a straight line, and the robot is doing its thing over time. And so we are counting these violations from the real traces of the robot, and we are basically following, but now automatically, we are following the uncertainty quantification process for what we are observing in the real world. And so then we are, the moment we have enough data, we will have statistical distributions for the violations observed in the field, and we have computed offline, we have statistical distributions of the violations computed in the lab. So we can compare the parameters of these statistical distributions, right? And we can then see, okay, well, something is not right because these parameters are deviating. And maybe this is the basis for predictive maintenance, where we could observe a gradual shift in these statistical distributions. So this is an example of what we can do having quantified the uncertainty from lab experiments. So where's the uncertainty propagation? So far we kind of left it implicit. We conducted these experiments with the robot, but each of these experiments is naturally, because we are really only looking at the events of interest, and these events are the result of uncertainty being propagated in the system. We have been doing uncertainty propagation, but it's just left implicit. So what happens if we try to make this explicit? Well, we'll first need to look into our system, look at the plant, look at the controller, and we start modeling our system, right? First, we start looking, what are the sources of uncertainty? Well, we've got wind that maybe shifts the robot. We've got GPS noise, so there's uncertainty in the GPS sensor, and we've got steering noise, so we can tell the controller to turn 45 degrees, but it's never going to be perfect, and so on and so on. There are so many sources of uncertainty that enumerating them becomes quite difficult. So then we start modeling, and that's where the benefit comes in. How do we model this? Well, in this case, we look into how is our controller built, and it's essentially a sort of a key, a P controller that just adjusts the error adjusts the steering wheel depending on how much the plant is away from the straight line. Don't bother about the details, and the kinematics of my plant is just a bicycle model. So where's the error here? Well, we have placed the error. You can find the error terms. We have measurement error, So whenever you observe a particular measurement from an angle orientation of the plant, we add a small error, and we claim that this error is white noise, is Gaussian. So on average, this is 0. It has a standard deviation. So we are making a statement about the statistical distribution of the noise, of the sensor noise, and we are also making a similar statement about the statistical distribution of the sensing noise, which is here represented here. If forget about the equations, it doesn't matter so much. What matters is really we have placed terms, statistical distributions in our model. So our simulation model is now a stochastic simulation model. It contains parameters for statistical distributions. And how do we use these models? Well, first we need to identify what are the actual parameters of these statistical distributions. And this is the typical method for uncertainty quantification. So we would go back and see, okay, what is the method we followed? That this is the method for uncertainty quantification. So we would have to define the events of interest are the noise in our sensors. And for example, if we are considering noise in the GPS sensor, then we need to conduct physical experiments, or we need to look at the manual of the GPS to tell us what is the statistical distribution of the uncertainty for this sensor. And we would put that in our model, right? So assuming we have these values defined for these statistical distributions, we can now start repeating the previous method of uncertainty quantification, except now we are propagating. We are explicitly propagating the uncertainty from our simulation model till our events of interest. So again, we define the events of interest, the same thing, it's just a copy of the previous ones. Now we perform, instead of physical experiments, we perform virtual experiments. So the idea is to use a random number generator that looks at the statistical distributions of the terms used in the stochastic simulation model, and runs and starts sampling, drawing values from those statistical distributions, and each possible sample leads to a simulation. We run simulation. And so here you can see we generate similar plots. And it's actually a very good idea that the plots look similar, because that means we've correctly identified the sources of uncertainty. If our simulations here do not match what we observed in practice, then we will not have the correct statistical distributions. So we perform our virtual experiments, and this is what I'm essentially doing is the Monte Carlo simulation method, right? And then we again count. So it's about the same. It's the same as the previous method, except now we are counting. So where's the uncertainty being propagated? It is propagated because we are now running a stochastic simulation model, and where each time a source of noise comes in, it's being drawn from a statistical distribution, and the simulation model is giving us the means to propagate that uncertainty. That is to giving us the means to measure how that uncertainty is evolving over time. And you can see, for example, this is not an example. The controller is acting, and the controller is doing a good job at handling all the uncertainty in the system. And that's why this stochastic simulation model is playing an important role. It's not just saying our car could drive left or right, because that would just, an uncontrolled car would just completely drift away. It would do a random walk, but it's not a random walk because the controller is battling that uncertainty. Whenever the controller is a feedback loop controller, and one of the jobs of these controllers is to precisely handle and mitigate the uncertainty. So we see some uncertainty mitigation. There is noise, certainly, but it's not as bad as it could be without the control system. Now we count the events of interest. We normalize those counts in order to obtain probability density functions. And then we again repeat the process, identifying a probability distribution and its parameters to the data. Right. Let me check the time. Yes. So where did the uncertainty propagation happen? Well, it happened because we went from statistical distributions of our sources of uncertainty identified, explicitly made in the model, to statistical distributions of the properties of interest, of the events of interest. And this is uncertainty propagation. Right, now I'm going to move into a digital twin, an example digital twin. It's yet another example. First, definitions. We adopt a definition of a digital twin when the data flows to and from an existing physical object and a digital object, and so on. This definition is unfortunately too broad, so usually we put the picture saying, okay, we've got a physical twin, we've got some communication medium in order for the physical twin to communicate with the digital twin. And then this is our digital twin, which is a piece of software that implements a number of services that are typically there to add value to the physical twin. Right. And we will I'll focus on this monitoring service and the self-adaptation service. And obviously the first part of the talk was mentioning how you could implement one concrete monitoring service using these statistical distributions. We'll look into an incubator system. It's got a fan, a styrofoam box, an insulated container. It's got a heater. It's got something to be fermented. In this case, it's tempeh, and it's got some sensors here. And ignore this stuff for now. So this is a CAD model of our system, and you see a diagram here. A controller is fairly simple controller. The state machine makes it more complex than it actually is. What really is going on is this is an open loop controller. So it's actually neglecting the values coming from the sensors. And it's got two important parameters which are made in bold here in the state machine. One is the number of samples for heating. And the second parameter is the number of samples per period. Typically, we fix the number of samples per period and will vary just one parameter. So this is a very simple controller. The idea is that the digital twin will do the heavy lifting of recognizing something changed, the controller is not performing as it should, and will, for example, update this parameter here, which will lead to a different signal profile, which naturally, this is about 50% of the time the heater will be on, and 50% of the time will be off. So we can vary to 100% of the time or 0%. I can imagine that some of you are already thinking, okay, why the hell are you using an open loop controller when a closed loop controller would probably handle quite a lot of propagation? And I fully agree with you. This is the point is to show this is just an open loop controller for illustrative purposes. We actually in practice use a closed loop controller, but it has more parameters, and those we know are also need to be updated as the system changes, because our process, the thing we are fermenting, tempeh, is complex. It's a biological system. No two batches are the same, and you can see the different stages in the process. It starts with well, first you need to put beans in a bag. They don't just show up. That would be magic. But then there is it's inoculated with some with a fungus, and then the fungus grows, eats some of the soybeans, and digests stuff that we typically do not like to digest, and so it actually increases the bioavailability of the beans. So we take more protein and nutrients out of the beans if we eat a fermented tempeh. There is nice work in studying the behavior of tempeh over time, and you can actually see here how complex the temperature profile is. And of course, this is not the same. We have been making tempeh in our lab, and sometimes it takes 24 hours maximum. So these really vary a lot. The shape looks like this, but it's not. The variance is quite high between tempeh. So as you can see, when the tempeh starts fermenting, when it starts growing a lot, it starts generating heat. So it actually starts generating heat. You can see the temperature here. It drives as much as 40-something degrees, and it likes ideally 37 degrees. So this is, we need to control this process properly. And because each batch is different, we need the digital twin to identify the characteristics of that specific batch and then adjust the controls for it. Architecture of our digital twin. We have, I'm using the C4 model. You can see the physical twin. This has a plant and an open loop controller. You can see the parameters of the controller here. The plant has, well, one variable of interest is the air temperature, and the heater can be on or off. Right, that's just a sketch of what the plant is. My open loop controller communicates with a digital twin via a RabbitMQ message exchange. And so do all the other digital twin services. They can communicate between themselves and with the controller, for example, to send a message to update the parameters of the controller. They do so via RabbitMQ. And we will see the common filter. It's represented here as a service. It implements the monitoring. The self-adaptation manager implements the self-adaptation. And we've got a utility service here who simply records. It just listens to everything that's going on, all the messages being here, and records them in a time series database, which then the other services can use for collecting historical data. So where is the uncertainty quantification propagation here in the incubator? One part where it is in the state estimation, as done by the Kalman filter. So what happens here is my controller sends a message to the RabbitMQ message exchange saying what is the temperature measured now, and what is the state of the heater. Is the heater on or off? So that's the message being sent here. Then this message gets sent back to the Kalman filter. The Kalman filter is listening to those messages, and the Kalman filter says, well, yeah, okay, but I'm going to fill in some things. I'm going to fill in an estimate of the temperature of the heater, because I don't have a sensor in my heater. You can go back. There is no sensor here in the heater, but it's a quantity of interest. We have from offline experiments, we have concluded that this is a quantity that's important, and it affects, because if the heater, even if the heater is off and the heater is very warm, it will continue to warm up the system. So it's something that's very important to know, and that's what the Kalman filter tries to estimate. Then it sends this message. It sends this estimate back to the RabbitMQ, and whoever is interested, in this case, a self-adaptation manager and the data recorder, will receive it and will do something with it. The data recorder will just put it in the time series database, and the self-adaptation manager could potentially trigger a self-adaptation. It's checking, is really monitoring these things over time. Another view on what is being measured and what is being estimated. We've got two temperature sensors in the box. In practice, what we're doing is taking an average of these two temperature sensors. So that's being measured. Then this is sent, and we know the state of the heat bed. We know if the heater is on or off. So those two things we can pass on to the Kalman filter, and then the Kalman filter is estimating the temperature of the heat bed of this little thing here. And also it also produces its own estimate of the temperature, of the average temperature here. Right. Usually these two are well aligned. So where's the uncertainty here? Well, we've got sensor noise, we've got the environment temperature, and so on and so forth. So again, identifying all sorts of uncertainty is an interesting discussion to be had offline. And then there's the modeling errors as well. You'll see soon that the Kalman filter, one of the inputs is a model of how the plant evolves. And so it will also, that model will also contain inaccuracies, which are also one source of uncertainty. Right, how do we use the Kalman filter to propagate uncertainty? First, the inputs to the Kalman filter are the Kalman filter already has an explicit representation of uncertainty. So it is possible to place this parameter that is the standard deviation of our measurements. If we've got 10 measurements, we will put 10 different standard deviations for each measurement. We can also place explicitly the standard deviation of our modeling errors. And again, we have to measure these. We'll discuss it later. And then we have the equations of the plant dynamics. And with these three inputs, we can construct a Kalman filter, which will then be will estimate how these given uncertainties change over time. So you can see here an example of plots. This is from a physical experiment that conducted 2 years ago. And you can see in the beginning, the Kalman filter had not seen much data. Right, the Kalman filter is collecting. It's a dynamical system in itself, right? It collects data and it updates its internal state, and its internal state includes this uncertainty as quantified until now. And so you can see the uncertainty in the temperature of the heat bed of the heater. You can see it decreasing over time as it sees more data, and it sees the data is in line with the plant equations. Then it builds more trust in this, and so this uncertainty decreases over time. I'll explain it here. Sorry, I need to explain what is in here. This is the average temperature as estimated by the Kalman filter. I'm not showing the average temperature as the data because the two are very well aligned. There's no point adding noise. And I have the heater on and off signal, which is just a dummy signal. Don't worry about the units. It just says heater is on, heater is off, heater is on. And you can see, okay, there's at least a good correlation between our process, our plant equations, which are really contributing big time for this, for the heat bed trajectory. And you can see when the heater is on, then it increases. When the heater is off, it's kept more or less stable, and then it increases, and so on. And then when the heater is off, it eventually starts decreasing. Note, by the way, that the heater starts being off here, but it's still transmitting heat into our box. And that's why the box temperature continues to rise for a bit. And that's why it's important to estimate the heat bed, the temperature of the heater. Okay, these equations are for a closed lid system. So how can we use, this is, by the way, how the Kalman filter can be used to propagate uncertainty. It is propagating the uncertainty over time, and we can observe how that uncertainty grows or shrinks over time. The plant equations were obtained for a closed lid system, so we run experiments with a closed lid and we identify the parameters of the model, and we fed them into the Kalman filter. So if we haven't yet described how to measure the uncertainty, or how to measure the measurement uncertainty, how to measure the process uncertainty. But assuming we have those, we will configure the Kalman filter. And the two things can occur. One is the measurement noise, the standard deviation of the measurement noise may be much larger relatively to the process noise. And that means typically the Kalman filter will use the plant equations more. The Kalman filter always attempts to reduce the uncertainty by combining the data coming in with its own uncertainty with its own internal process uncertainty that he is estimated over time. And so if the process noise is much lower than the measurement noise, then the Kalman filter will typically trust the equations more, which can be a problem because if we open the lid, or if we slightly misplace the lid of the incubator, or if we place a batch of tempeh, or if tempeh starts to ferment and starts warming up, then our equations are actually wrong. And we will be able to see that if we compare the average temperature as measured by the sensors with the temperature as estimated by the Kalman filter, because the Kalman filter is trusting my model more, it will start misbehaving the moment we open the lid. And that can be used as the basis for anomaly detection. And here I'm plotting these confidence intervals around as estimated by the Kalman filter and from the data. And we can even use these confidence intervals as a way to trigger when are we really outside the confidence interval of the two signals, where we can decide, okay, this is something is definitely up. Good thing is, if we then close the lid, eventually the Kalman filter is always trying to make these two things align, and so it eventually will reach a good state again. So this is how the Kalman filter can already be used as a monitor service for a digital twin. If the measurement noise, on the other hand, is much lower, so if we've got good quality sensors than our process noise, then the Kalman filter will typically trust the sensors more and neglect more the equations. And for example, in this example, if I open the lid, then you can see it trusts the data so much that it doesn't even leave the confidence intervals of the two signals. Right? So the balance is really, how do we make, one hand, if we just want to do anomaly detection, we can blindly set these two values in order to do this anomaly detection. This is what they did the first time. Let's be honest about it. But if we can now look into ways to measure, to quantify these uncertainties, then we can obtain a much more reliable monitoring service, which we can then use to really detect anomalies or not. So how do we quantify these two quantities? First one is relatively easy. Measurement uncertainty. We've got sensors. For example, this is the temperature sensor used in the incubator. So we can look at the data sheet, and it says, for example, plus minus 0.5 accuracy within this range, right? Which you can then, we sort of have to take it, okay, what does it mean to plus minus 0.5? We can produce a Gaussian distribution out of this with a standard deviation of this value, and then we'll use it, for example, for the Kalman filter. Another way is, again, conducting experiments, right? Place the temperature sensor in an environment in which we know the temperature to a very high accuracy, and then we measure the results. And we will, again, obtain statistics on the results and statistical distributions and so on. Process uncertainty. It involves some more steps. First is, it's tied, this process is tied to the process of estimating the parameters of the model and how successfully we can estimate the parameters of the model. So the process is summarized as, these are all the parameters of the model. Don't worry about what the equations do. These are all the parameters, and what we're going to try and do is, well, we'll conduct some experiments. This is where the historical data comes in. We conduct some experiments. We then generate trajectories of this simulation model for a particular choice of the parameter values, and then we will compute the error between those trajectories and the data, and then we'll repeat with better values for the parameters. I'm describing gradient descent, but I could be using any other optimization method to figure out what the next guess for each of these highlighted parameters is. All the other variables come from the historical data. This is an example. We could start, the optimization process may start with, you can see the orange, which is the plant equations with the current guess of the parameters, does not very much match with the blue one for the temperature. We don't have a reference point for the temperature of the heater. This is just a simulated temperature of the heater. There's nothing we can do about it. We don't have direct measurements, but we can try and align the temperature with the average temperature from the data. And that's what's going on. In this case, the parameter of change is the capacitance of the air. So we can increase that value, and you can see it starts aligning nicely, and we can continue to increase until it has an almost perfect match. Right, and that's when we are done. And this is just an example for one of the parameters, but we have 4 parameters in these system of equations. When we are done, what we typically get is an optimal solution, the values of the parameters that produce this best fit, but we also can calculate the average error over time. of our model, and the standard deviation. So, and typically what we will get if the calibration process was successful, it will typically be the error will behave as a Gaussian distribution. So this nicely fits into our process uncertainty of the Kalman filter. There's a small detail here. This does not necessarily have to be the exact same value you place in the Kalman filter, but the idea is this value is strongly correlated with the noise that you're going to put in the Kalman filter. And current subject of research is what is this correlation factor, and how do we go from this to Kalman filter? But intuitively, we can see it this way. If I have a set of equations for which the fit is really not that good, that is, the standard deviation is quite high, I don't want to tell the Kalman filter that the process noise is very small. I want the Kalman filter to trust more the data because my equations suck, right? So now we'll take a broader view because we're running out of time. I'll take a step back and look at self-adaptation. So we've been only looking at monitoring. This is an example of self-adaptation in case for the incubator where we open the lid. After some time, we open the lid, and you can see actually the orange line, which is estimated by the Kalman filter, is actually following this fairly well. And that's because we are already updating. We are the digital twin is at work and is the self-adaptation service is updating the parameters of the Kalman filter for the plant equations, and it's also updating the control policy. Remember, this is an open loop controller with only one parameter, really. And so you can see it actually makes the controller work a little bit harder when I open the lid, and then when I close, it repeats the process and makes the controller work again. And the idea is to keep the temperature at 40-something degrees. And the reason, in the discussion, we can discuss why is it that the self-adaptation did not turn the controller on all the time. And there's a good reason for that, but I will not explain the specific self-adaptation process we are using here. Schematics, the self-adaptation can be summarized as a MAPK loop. The first, imagine we are roughly here and we are monitoring. So we are using the Kalman filter as a monitor and as a basis for detecting anomalies. We saw it in the previous slides when, like this. So we know when the lid opens, the Kalman filter will shoot off the edge compared to, so the difference between the Kalman filter estimated temperature and the real average temperature will at some point exceed a certain threshold. So we detect an anomaly. Then the system is left to, we have to leave the system to operate for some more, so we can actually gather enough data of the anomaly of the open lid system. Once we have enough data, we can now use the data gathered as an experiment to estimate the parameters of the model. So it's as if we're running a calibration online. And then if we are successful with this calibration, with this online calibration, notice we fell off the edge here. We let the system run for a bit and completely neglect the parameters of the outputs of the Kalman filter. We cannot trust them. But once we've collected enough of this blue line, we can start trying to fit the plant equations to this new blue line. And we find new parameters, new optimal parameters for this behavior. When we find those optimal parameters, we are at this stage, where we can start trying to figure out what to do about the controller. And this is where we can run many simulations with different parameters for the controller into the future to try and figure out what is the best control policy from now on. And assuming this is another optimization process, assuming we are successful, we can then update the control parameters. Right. if we decide to plot the intermediate calculations, the intermediate calibration, then if you zoom in on this area, what you really see is this edge, right when the Kalman filter starts failing. And then what you see here in green, it's a slide, it's very hard to see, but there is a green line here, which is really representing the new fit, the new calibration of the plant to the new behavior. So this means we have successfully found a new parameterization of our model of the plant. And then you see this jump here. This is when we reset the Kalman filter to tell the Kalman we have to rebuild the Kalman filter with the new plant equations. And then from here on, he's almost perfect with the behavior. Before progressing, before moving here, there has been an update into the control parameters. I'm just not displaying them here, but you can see it back here. There's been an update in the control parameters. In the same way, over here, it's easier to see. You can see the different simulations into the future of the new control policy. So when I'm here, what's happening is the self-adaptation manager has found new parameters for the plant and is now trying to figure out look into the future. The recalibration is looking into the past and trying to explain the past, trying to find better parameters for the past data. The control policy optimization is future oriented, right? It's looking at the future and running many different simulations of my system with a controller, with the new plant equations and the controller coupled together. And he's trying to find out, okay, what is the policy that will get me to my objective, whatever that is. And you can see there's different attempts. And then eventually it settles on the optimal attempt that you cannot see because it's overlapping the orange line. And so when it does, it resets the controller, the control parameters. So where's the uncertainty in this thing? First, we have seen that we have uncertainty in the managed element, right? And the Kalman filter can help us move that uncertainty, propagate that uncertainty from the managed element into our monitoring phase. So we've got those uncertainties coming out of the Kalman filter, the process and measurement uncertainty. We then, what we've seen is we have, when we run an optimization process for the calibration, we are getting as an output, we are getting an optimal solution of the parameters, but we can also compute standard deviation for the error of that optimal solution. So we have a way to obtain the uncertainty, the process uncertainty for the newly calibrated model. Then we need to make our control policy optimizer. So the guy who looks into the future and tries to figure out what is the best control policy, it needs to be made aware of this uncertainty, because currently it is not. Currently it trusts entirely on the new plant equations to figure out what the optimal control policy it is. And intuitively this doesn't make sense, right? If we had a new situation in my system that my plant equations don't quite fit well because maybe the system fundamentally changed, right? I moved the whole sensors into I moved it into the bathroom, or I just removed them out of the box, or I put them in a place that doesn't make any sense anymore for the plant equations. Then doesn't make much sense to spend a lot of time trying to find an optimal control policy. Right, so intuitively, we have a few knobs we can turn in this optimization process, right? Typically, when you run these optimization processes, you can say, well, I want you to really try and find the optimal solution. My tolerance for what is optimal is very, very small. But so I can adjust this tolerance based on the uncertainty that I have estimated from the newly calibrated model. That's one opportunity. Another opportunity is, of course, to propagate this uncertainty from the newly calibrated model into the optimal solution of the new control policy. And then pass that uncertainty on into the controller. And maybe if we're using something like a robust control or so on, we can have a control system that is actually aware of the uncertainty in these parameters, in their own parameters. So these are my thoughts on where uncertainty can play a role in self-adaptation and current subject of research. Don't think I have more. I would like to discuss this with you. Thank you very much.
Well, thank you very much, Claudio, for your talk.